Well, I got a little confession to make. I'm a little frustrated. I'm not at any of you. No, you guys are awesome. I'm just frustrated because I really like circles. And I think they're super cool. This is one of my favorite sections of the year. And it just seems so disappointing, I guess, to have to teach it to you this way. Because you probably know how I get when I get excited about something. And I think this is really cool. And I love doing these problems. And I love going over these problems with you. And we're not going to get to other than if you want to call me up, we can talk through some of this stuff. Otherwise, it's just me here showing you how to do stuff. So here we go. I will overcome my frustration. We'll get through this. Good news is this is going to be a fairly short lesson in the sense that what I have to show you isn't going to take very long. But then I'm going to spend a little bit more time doing a couple of homework problems with you and for you, because I think that's where the complexity of this concept really comes in. So you can see on the screen that the theme is inscribed angles. And I know some of you get the shakes when you see that word inscribed, because you're like, oh, remember we did triangles inside circles or circles inside triangles. Wasn't maybe the best memory for all. This is actually going to be okay, I think. So what I want to do is take a circle here and just remind you what the types of angles we've looked at previously look like. This was what we called a central angle. So this right here, called a central angle. And not trying to be funny here, but because it's formed literally at the center. There's another kind of angle though, and I'm gonna, I think I'll put it here. If we take a point that is on the circle, instead of being at the center of the circle, and we draw lines, I'm trying to draw straight lines this time. We draw lines that cut off an arc. Then this angle, I'll label it as Y here, has a different name. We call this inscribed. So an inscribed angle is one that is formed where the vertex is on the circle, and the central angle is one that's formed when the vertex is at the center. Now you notice in this case, both of these angles are cutting off, we have a better term for it than that, but I'll use cutting off the same arc. This arc is called the intercepted. So we've already covered the fact that the central angle here will equal the measure of the intercepted arc. What we're going to look at today is how this angle relates to that arc. And I'm just going to show you, again, this is on your theorem sheet that I handed out to you. This is the picture we're going to use here. So you can see, first of all, in the drawing that the inscribed angle is formed with the vertex on the surface of the circle, and then the intercepted arc is the arc on the other side. What's important and interesting about this is that the inscribed angle measure is always going to be exactly half of the arc that it intercepts, half the measure of the arc. You might be thinking, does that make sense? Why does that work? I'm going to show you, I see there, obviously there's some corollaries coming here, but let me show you what this looks like when I draw this out. So I'm going to give you two very, very simple examples. Draw right here. And the first one is going to be using a diameter and, for lack of a better term, a tangent. So I want you to look very, very carefully at the relationship between this angle and that arc, okay? We know that this angle is 90 degrees. But this arc makes up half a circle. It's 180 degrees. I haven't proved anything to you there, but I hope you do see that there's a case where a 90-degree angle actually creates exactly half of the entire, well, circle, 180 degrees. Now I'll show you another one that is not nearly as exciting, but I think we can use it to illustrate this. That's it. That's the angle and that's the arc. And you're like, okay, well, what angle, what arc? I totally understand. This is the angle right here. Oh, just kidding. This is the angle right here. It's 180 degrees. Right? Straight line. We know all about straight angles, right? And it cuts off an arc that goes from here all the way around to here, also known as 360 degrees. Again, it's half. So here's what we come down to. The angle, as we start an angle, maybe I can do this. As I start an angle, just kidding. I start an angle down like this, starts at 0 degrees, and it's slowly going to cut off more and more of the circle. That's actually going to cut off 90 degrees of the circle, but it's 45 degrees the angle. I go to 90 degrees, I can get bigger angles, but the biggest I can get is 180 degrees. That's it. But in the process, I'm actually intercepting the entire 360 degrees of the circle. And so it's not a proof, but I hope it makes sense that, I'm going to switch back for just a quick sec. Hope it makes sense that the measure of an inscribed angle is half the measure of its arc. Remember, I told you that the teaching part of today is going to be pretty short and, in theory, pretty easy. It's the doing the problems that's going to be really, really complicated. So I'm going to spend a little bit more time on that in just a minute. Now, there's a couple corollaries as well, and I want to highlight these. First of all, it shouldn't surprise you that if you have two inscribed angles and they both intercept the same arc, well, they're both angles will be half the measure of the arc. So those two angles have to be congruent. It would be, well, I won't show you that quite yet. An inscribed angle that cuts off a semicircle is a right angle. I showed you that. That was the first example I showed you where we had a 90-degree angle and it cut off half the circle. But also remember that half the circle is a semicircle and the line that produces that is a diameter. So basically, if you have any inscribed angle, actually, I'm going to draw this up. This is worth taking just a second. You see how I get excited? I like this stuff. Let me draw another circle here. So now I want you to imagine that we've got a point sitting right here. And we have a diameter that goes like that. And to be clear, it goes right through the center. So wherever I put this point, the question is about this angle right here. But you see that it's cutting off or intercepting 180-degree arc. So this has to be 90 degrees. Even if I were to put it over here, like to move that point over here, so that now I'm looking at that as my angle, this is still a right angle because it still cuts off this, well, this, oops, it still cuts off this half circle. So any angle formed anywhere along this side of the circle that has its endpoint on either end of the diameter is going to be a right angle. That's kind of the idea. I think it's kind of cool. I mean, you don't think it's going to happen, but it happens. And this one is a little bit unusual too. Opposite angles of a, wait a minute. I thought we were doing circles here, man. I didn't know we were doing quadrilaterals. We've already put that one away. Yeah, but wait, this is cool. Opposite angles of a quadrilateral are always supplementary. How is that possible? How is that possible? Well, let's think about this. I'm going to actually just zoom in right now on this right-hand drawing right here. This one right here. I don't know if I can show it. But what I'm talking about, oh, you know what? Here's what I'm going to do. Oh, look how fancy I am. This right here. Now I can write on this. Okay, so this is what I'm talking about. And now I want you to look at angle A. It cuts off an arc that goes here. Okay? I don't know what the arc is. I don't know what the angle is. But if I were to change this, watch me, wait for it, and I look at angle C instead. See my colors? I chose the right colors. Angle C now cuts off this arc. And I don't know what that arc is. So I don't know what C is either. But I know that C is half of the yellow, A is half of the purple, and purple plus yellow make 360. So half of 360 have to be 180, so A and C have to equal 180. Yeah? Let's try it again. Try with different colors now. What about angle D? Angle D goes from here to here, and it cuts off this arc right here. And then angle B, I'm going to go back to this one because this is a cooler one. Angle B here cuts off from here to here, and I get this whole arc here, and blue and green make 360. So B and D, which are half of blue and green, have to add to 180, therefore they're supplementary. And oh my gosh, if B and D, oh my gosh, wait, are you serious? If B and D add up to 180, and A and C add up to 180, what does that mean that A plus B plus C plus D add up to? 360, right? Almost like 360 degrees in a quadrilateral. So if you drew a quadrilateral inside a circle, you still get 360 degrees. Geometry, man. It's great stuff. So that's it. That's actually, whoa, that's like the end of the this section. What I want to do is I want to look at a couple of homework problems here. So I'm going to, oh boy, what do I want to do? I don't want to do that. I have caused a bit of an issue here. Hang on just one sec. Okay, here we are. So what I want to do is do a couple of your homework problems here for you. I'm on page 448. We're going to do in order 5 and 8 on one drawing, and then 9 and 12 on the other. Okay, so let's start with 5 and 8, and that might be all I get on this page. I don't know if I can do all. I think I'll just keep it like that. Remember I told you, this is where it gets really, really complicated. The whole concept of the theorem, okay, fine. But it gets really complicated when you start doing this. So I'm going to take and draw some, remember the term, right? These are chords. I'll put the center right in the middle. This is point Q. I really want to take my time here, so I'm not going to rush it. What else are you going to do? I mean, there's other things you could do, I guess, but It's not terrible sitting here, maybe. By the way, at least this way you can get up and walk away. If you get tired of me, you can pause me. But in class, I just yammer. So this is gonna be a little bit better, maybe. All right, 120 there. This is 49 here. And by the way, you'll notice that there's 4 problems in the book on this drawing. I'm only going to do 2 of them because I don't want to take all the fun away from you. These drawings also go there. And we have an arc that measures 46 degrees here. And that looks like it's it, right? So number 5 is asking for the measure of arc JKL. So JKL is this one right here, yeah? So ponder that while I write up the other one, which is going to be number 8. That's asking for the measure of angle KLM. KLM is this angle right here. So there you go. And I wanted to pick one of each so you could see what this process looks like. So let's go through this together. Arc JKL is intercepted by this inscribed angle, 49 degrees. So 49, based on our theorem now, is going to be 1/2 of the intercepted arc. And then, of course, we know we multiply by 2, those cancel. And measure of arc JKL is 98 degrees. 98 degrees. That was a thing once, maybe remember. Somebody's going to make a comeback, I thought. It's either in sync or 98 degrees. I don't know. I'm sure one of you will let me know. Okay, so this is 98 degrees, which means this is going to be 52 degrees, because I know how those add up. And now this is kind of interesting, because the other question is, what is KLM? KLM is this angle right here, and that cuts off this arc here, right? KLM cuts off that arc right there. And I know that this is 1/2 of the measure of arc KJM. And I'm putting the J in there because I don't really know if this is more than half the way around or not. So I'm just going to put in there. It looks like it could be almost just a half circle. So if you think about this picture, though, we've got 120. This together makes 98. That's 218 together, right? I add 120 and 98. I just add 100 and I take away 2. So that's 218. This has to be the rest of the circle, which is 360 minus 218, which is 142 degrees. So this arc is 142. And then if I look at the inscribed angle, this is going to have to be 71 degrees. What do you think? That's kind of a lot of work, isn't it? But you're going to be able to play around with 360 degrees around the circle, and then pull out each of these little inscribed angles, figure out what the intercepted arcs are, and you can start putting the pieces together. I really like these guys. I hope you should do too. We'll see. All right, let's look at 9 and 12 now. So again, we're page 448. This is 9 and 12. And the drawing is a little bit funky here, so give me just a second. I'm going to get this right. If you want to take a second and copy this down, that's actually a really good thing to do. It can be really useful. Got that. I have a chord there that's missing, just so we know, the center, which again is Q. Another chord that goes this way. And let me start labeling some points here. This is J, this is H. What the heck, what is G doing over here? There's G, here's E, there's F just hanging out on its line, and D's over here. And then we have these, K's over here too, sorry. We have these measures that are kind of unusual. 72, but 72 degrees is just to be clear, it's the angle between this chord EH and line EF. That's why I want to do this. It's a little bit confusing. This is 106. Okay. So number 9 is asking for the measure of arc EGH. And number 12 is asking for the measure of angle DEJ. So let me just lay this out here. I'm going to put it in green, what we're trying to find. EGH is this arc right here. And I would tell you that it is intercepted or formed by that inscribed angle. And yeah, that's an inscribed angle. Even though this line is tangent and goes outside, this kind of goes back to this drawing over here, where you can have a line that goes outside the circle and still have it create an angle. So this is actually pretty easy. Because we know the inscribed angle is half the arc. This is just going to have to be twice 72. It's 144 degrees. So this is 144. So now I don't want to get too far ahead of myself, but I'm noticing that I've got this arc and this arc. Together they make 250. Yeah? 106 and 144 make 250. That means that this arc right here only has 110 degrees left. Now, why do I care about that? Well, in general, I just wanted to know things, but curiously enough, this question is asking for this arc right, this angle right here, which is going to be half of the arc it intercepts. That's got to be 55 degrees. Just 1/2, 110. So this is 55. Now, if you can hang in there just a few more seconds, I want to show you something I think is cool. The only thing we're missing along this straight line is this angle right here, right? But I know that that angle intercepts this arc. So if I take half of that arc, I'm going to get 53 degrees there. Now, why is 53 interesting to me? Because if I take 55 degrees, that's this angle, and 53 degrees, that's this angle, and 72 degrees, I get, it's 108 plus 72 equals, shocker, 180 degrees. I have 180 degrees across that straight line, which I expected, and the sum of all the arcs that 180 degree angle produces or intercepts is 360 degrees. It all just fits together. How great is that, huh? So look at the calendar. Today's Friday. Hey, happy Friday. Happy kind of spring break. You're gonna have assignment today from page 448. I don't have it handy, but you can look online, look on your sheet and get it. Next week is technically going to be like spring break again. You may have teachers working, but we sort of have to take a spring break at some point. So we're taking a spring break. There'll be some work posted online if you want to do it, but you won't be hearing from me during spring break. Unless you miss me and you want to, then you can get a hold of me. I'll be around. So we will actually pick up again on April 13th, which is when we would have come out of break. And I think the next lesson I'll have for you, I'll just make this next lesson, is April 15th. And we're going to be wrapping this up somewhere right around the 22nd, so the end part of April. So hope you're well. Have a great break, whatever that means. I don't know, you can't really do anything different, but send me your questions. I enjoy these circles. They're kind of fun. See you later.